Math 287. Quest to College, I'm Joe Vasta. We are going to cover section 8.1. That's a whole new chapter. So let's see what we're asked to do on our homework. Linear differential equations, some theory. So we've covered some linear differential equation first order in chapter 1, and we would use the method of integrating factor. But once you get to higher order, you're going to end up having some problems. Okay, it's going to get more complicated. So, problem number 1, they give you a linear transformation. So this is weird. You might have thought we finished with linear algebra, but we're going to use linear algebra in this section. The linear transformation goes from C3 to C0. So, if that kind of scares you, let's see what C3 is. C3 is the vector space of all real valued functions that are continuous and have at least 3 continuous derivatives on an interval I in the i's, it's in on the real numbers. So this is an infinite dimension vector space. Something that would belong to C3 would be the sign of x and polynomials and things like that. C0 is real valued functions that are continuous, okay, and have at least 0 continuous derivatives, so they're just continuous functions. Now, D is something called the derivative operator, and the only way to really describe it is to show you how it works. It really is just a derivative. So the transformation is described by saying d cubed plus xd. They want us to find t of e to the 2x. So e to the 2x is a vector living in C3. And we're going to send them over to another world by using this linear transformation. So how am I going to do that? Well, let's write this out. T of e to the 2x. Okay, so this is going to seem weird the first time you see this, but I'm going to go ahead and replace the t with d cubed plus xd. I'm going to put parentheses around it, and I'm going to say that this is going to operate on e to the 2x. Now, we got to be very careful with our notation here. Okay, so I have to write d cubed to the left of e to the 2x. And so that's what I'm going to do. And then I'm going to write x d e to the 2x. So hopefully, I think someone's doing some weed trimming outside. Hopefully that's not affecting the sound of the video. I'm doing this at home. It's a Saturday. I should be not working, but I'm working because I have to have these videos up before the day comes. So notice, I got to be extra careful on this. I can't just go ahead and say, well, let's just put this x over on the right side of the d, because it's not on the right side of the d. So position is very important with the derivative operators. Okay, so what am I going to do with the derivative operator? This is like having 3 d's. You're really just taking the third derivative of e to the 2x. So off to the side, I'll say y equals e to the 2x. The first derivative is 2e to the 2x. The second derivative is 4e to the 2x. And the third derivative is 8e to the 2x. So you hit this with 3 derivatives, you end up getting 8e to the 2x power. And so that's what this becomes. Now, I'm going to write the x there because the derivative operator only operates to the right. And so I'm taking one derivative of e to the 2x, which we see is 2e to the 2x. Now that the derivative operators are gone, I can rearrange things, and that's what I'll do. I'll go 8e to the 2x, that guy we keep like it is, and I'm going to put the constant out front, which is something that we usually do in math, 2x e to the 2x. And so there is a function that we got when we put e to the 2x through the linear transformation. So we have e to the 2x, and this is the result. Now, it was important for this linear operator that we could take 3 derivatives, and that's probably why we are coming from C3, because we want the at least 3 continuous derivatives on the interval. Let's go ahead and do another problem that involves this same linear transformation. Okay, so problem number 2. T equals d cubed plus xd. Find t of x to the 4th. So let's write that down. I'm going to replace the t with d cubed plus xd. That's going to operate on x to the 4th. Okay, so this is d cubed x to the 4th. It's very, very tempting to write this as dx to the 5th, but we cannot because this x is to the left. So it has to be x dx to the 4th. So now I have to take some derivatives of x to the 4th. So the first derivative is 4x cubed. The second derivative is 12x squared. And the third derivative is 24x. So right here, I can replace this. d operates on x to the 4th. It 3 derivatives gives me 24x. And over here I have plus x times the derivative of x to the 4th, which is 4x cubed. So let's go ahead and write our answer really nicely. So it says 24x plus 4x to the 4th. And that is our final answer. You can factor out a 4x if you want. I'll just keep it like this. So that completes problem 2. Why are we doing this? This seems weird that we would want to even do this, but you're going to actually see how this helps us understand differential equations. So I'm going to do something kind of weird here. I have the first 2 problems, and you know they got sent through the linear transformation, and these were the results. Now what I'm going to do, here's the same linear transformation. I'm going to ask you to find t of e to the 2x plus x to the 4th. Now remember what t is. T is a linear transformation, which means you can do all the things that you want it to do when you first learn functions. Because it's a linear transformation, it has these linearity properties. Look at that. You can do that. And you can also do t of 4x is the same as 4t of x. Okay, so that's what we're going to do here. We're going to write this as t of e to the 2x plus t of x to the 4th. So this one right here, we've already computed up there, and that's why I wrote that down. So we have 8e to the 2x plus 2x e to the 2x. And then I have t of x to the 4th, which is this right here. So plus 24x plus 4x to the 4th. And there's the answer. And so, that's how you do these linear transformations, these weird ones with the derivative operators. Let's go ahead and do problem number 4. Now, problem number 4, I'm going to throw some weird notation at you. It's just a little different. We have a new linear transformation. I'm not going to call it t, I'll call it L. It goes from C2 to C0, and it looks like this: d squared minus 3d minus 4. I have a function y equals x squared, and they want us to find Ly. Now that looks different than what they've been asking us to do. What they've been asking us to do is do something that looks like this: L of y. Or we could write this as L of x squared. So this notation is the notation that they use sometimes with these linear transformations. And all it means is this: L is d squared minus 3d minus 4. That is going to operate on y, which is just an x squared. Okay, so let's go ahead and distribute. We have d squared x squared minus 3d x squared minus 4 x squared. Okay, the second derivative of x squared would be, let's see, the first derivative is 2x, the second derivative is 2. Then we have minus 3, might as well just write this out. The derivative of x squared is 2x. And then we have a minus 4x squared. So this looks like we have 2 minus 6x minus 4x squared. And so there's our answer. Let's go ahead and do another problem that uses the same linear transformation L, and we'll pick a different function. It won't be x squared. It will be e to the negative x. So maybe you want to see if you can do this on your own by pausing the video and then start it up and see what I get. Okay, so on this one right here, I'm going to go Ly equals, L is d squared minus 3d minus 4. Y is e to the negative x. Okay, so this is d squared e to the negative x minus 3d e to the negative x minus 4e to the negative x. Okay, the second derivative of e to the negative x, well, the first derivative is a negative creature that looks like that, and then the second one is actually going to be two negatives, which is going to be e to the negative x. So e to the negative x minus 3, the derivative of that is going to be negative e to the negative x. Then we have minus 4e to the negative x. So this is e to the negative x plus 4e to the, that's not 4. Let's see if we can get this. It's been a while since I used this here. Look at that. Plus 3e to the negative x, and then minus 4e to the negative x. And look what happens here. What we end up getting for our answer is we end up getting 0. Now in terms of linear transformations, so we are doing a linear transformation, whoa, that looks like this. And the first function we did, so you can look back at number 4, it was x squared. It got mapped to 2 minus 6x minus 4x squared. This guy right here, which was e to the negative x, it got mapped to 0. So what can we say? This is a linear transformation. What can we say about this blue guy? That this blue guy, I'll write it in blue here. So we're done with this problem. E to the negative x squared is an element, so that's what is an element means. Looks like is an element of the kernel of the linear transformation. Remember, the kernel is the set of vectors in the domain that get mapped to 0, whereas x squared is not in the kernel of L. So that's interesting. So you know what we're going to ask you to do on the next problem? We're going to give you this linear transformation, same one, and I'm going to ask you to find the kernel. So let's do that. Here's a linear transformation, and we are to find the kernel. How do I find the kernel of the linear transformation? The kernel happens to be all functions y, where Ly will equal 0. So some of you are like, the kernel, he's right there, but we have to say what that is. What is that kernel? Well, we don't know what it is. We're trying to find it. So I'm going to replace L with a d squared minus 3d minus 4. I don't know what that y is, so I'll just write it like that. This equals 0. Okay, let's go ahead and distribute d squared y minus 3d y minus 4y. This equals 0. And what is the second derivative of y? The second derivative of y happens to be, let me look here, I don't know what it is. Oh, I know what it is. It's y double prime. Okay, and we have minus 3 times the derivative of y, which is y prime, minus 4y. This equals 0. What does this look like? This here looks like a second order linear homogeneous differential equation. And anytime you solve a second order linear homogeneous differential equation, you are actually finding the kernel of some linear transformation. So we would have to know how to solve this. And the funny part about this is we can't do this problem. So here's a problem, problem number 6, where the answer is we cannot do this yet. Okay, so we don't want to get in the habit of writing that on our exams now. So what do? We just throw that to the side. Let's go do another problem now. So this is working out pretty good. So here is another linear transformation defined by a derivative operator, and we have d minus 4. We are asked to find the kernel of this linear transformation, which I call J. So J of y is 0. I'm trying to find the y's where that will happen. Okay, so J is d minus 4. That operates on y. This equals 0. dy minus 4y equals 0. The derivative of y is y prime minus 4y equals 0. And we have a first order differential equation. It looks like we can solve this, and I think it's separable. Let's go ahead and solve this. Y prime equals 4y, and then we have dy, it is separable, over y equals 4 dx. Integrate both sides. I end up getting, we'll take the work up here, ln absolute value y equals 4x plus c. I'm going to e both sides, or exponentiate both sides, and on the right hand side this thing goes pop. I have absolute value y equals e to the 4x times e to the c being another constant, and that c can absorb the absolute value. I have y equals c e to the 4x. And this solves the differential equation. So if this was just written as the differential equation, solve this differential equation, then there's the answer right here. However, this was, we were asking to find the kernel of J, so it's all these creatures here. And on the right-hand side of this equation, it does look like a linear combination of just one thing. So the kernel of J is going to be the span of just one function, it's going to be the span of e to the 4x. And so now we're talking linear algebra with the span and all that stuff. What your book is going to do is your book is going to write the kernel as c e to the 4x such that c is an element of R. So they're going to use the set builder notation only just because they're amateurs. Here we have this great notation that we learn, and they teach it in their book, yet they're like, oh, let's go back to this because we're feeling maybe insecure with span. I don't know what it is. Anyway, both are acceptable. So the main thing, so we're done with this problem. We're finished. So I'm just having a math nerd moment. The dimension of the kernel of this linear transformation happens to be 1. Because there's only one element there. This is a linear combination of only one seed. So that's 1. The dimension of the kernel of L, and you're like, what is L? L is from the last problem. What do you think that dimension is going to be? Well, what's going to happen, since this is degree 2, or this is an order 2 differential equation, it's actually going to be 2. So this L was last problem, in case you're looking at the PDF. So it's 2. And so we know what the dimension of the kernel is going to be, because it's going to be the order of the differential equation, or the degree of this linear transformation when you see it as a polynomial. And so there it is. Now problem number 8, what we want to do with problem number 8 is we want to go back to the one that we couldn't do, and now we're going to be given a hint. So, you know, on problem number 6, that's the one where we answered, we cannot do this yet. We also answered the fact that we know that the kernel has dimension of 2, and this was just like something we don't know how to do. But we're going to help us. I'm going to help us along by asking this question: is there a function whose derivatives include the same function? Because look at this, we have y, and then you have y prime, and you have y double prime. And if the derivatives include the same function, then perhaps when you plug that in there, you'll end up getting 0 equals 0 if those all cancel out. So yes, there is. So I think we could say the one that comes to mind is e to the x, the Superman of all functions. You zap it with your derivative gun, it's e to the x. You zap it 27 times with your derivative gun, it's e to the x. By the way, later in this chapter we'll learn how to kill Superman. Okay, so let's go ahead and plug this into the differential equation, because we may have just found the solution. Y prime is e to the x. Y double prime is e to the x. I'm going to plug this into the differential equation, so that one right there, and I'm going to get e to the x minus 3e to the x minus 4e to the x equals 0. So this is really negative 6e to the x equals 0. No, we guessed wrong. Okay, let's take another guess now. Maybe something that might work is if you had not just e to the x, but e to the rx, because its derivative is also going to have an e to the rx in it. And so let's go ahead and take some derivatives. Y prime is r e to the rx. Y double prime is r squared e to the rx. I'm going to plug this into the differential equation. We're going to see what we get. So when I do, I end up getting y double prime, which is r squared e to the rx minus 3. So I'm plugging these guys in here. So minus 3y prime minus 3 y prime, which is r e to the rx. And then I have minus 4 times y, minus 4 e to the rx. This equals 0. Okay, so I have this equation here. I'm going to go ahead and, well, I'll make the realization on the left-hand side that there's an e to the rx in all the terms. I'll factor it out. And I have r squared minus 3r minus 4. This equals 0. Okay, well, this e to the rx can never equal 0. It doesn't matter how hard you try to think of what value would make that happen, but it will never equal 0. And so, look what we have. This guy right here has to equal 0. Now look around. Look around this piece of paper here. Where do you see something that reminds you of r squared minus 3r minus 4? Right up there. D squared minus 3d minus 4. Look at that, it's the same thing. So the next time we get another one that's similar to this, where it just has d's and constants here, we can jump right to this. Now this thing has a name. This polynomial is called the auxiliary polynomial. Auxiliary. I always hate spelling that word, polynomial. And any guesses on what this equation is called? I'll circle it in purple. And maybe you've guessed what it is called. This is called the auxiliary equation. So the auxiliary equation is gotten, you know, by doing this development here, but it will, you can always get it from up here. Now, what are the r values? The r values, I think I will go to another piece of paper. So I don't want to, maybe, I don't know how much more writing I have. I'm going to go ahead and write this down again. I'm going to try to factor it. It is a Saturday that I'm doing this, so I might not be able to factor this. Maybe that's my weakness, is Saturdays. I don't know. No, looks like I could still factor on a Saturday. Okay, so it looks like r equals -1 and r equals 4. Okay, so what is this all about? Okay, so I know we can't fit everything on here. It just means that, remember, is there a function whose derivatives include the same function? There is. There's actually 2 of them. One of them is this, y equals e to the rx, so this is going to be to the -x. And then the other one is y equals e rx, so this is 4x. Those both solve the differential equation. One is not a scalar multiple of another, and if you're thinking of these as vectors, you can see that these 2 vectors, e to the -x and e to the 4x, are independent. Not only are they independent, they are going to form a basis. Okay, so let's move this back over here. I know we're covering up some of the things, but this is the important part right here. These guys are, they form a basis for what? The kernel of that linear transformation. So the kernel of L equals the span of e to the -x and e to the 4x. Both of those are, you know, those are independent. You can see that. With 2, you just have to check to see if they're scalar multiples. But if you want to run this through the Wronskian and show that it is non-zero, go knock yourself out. And so this guy right here, let me maybe use some colors here. When it's asked like this, then that's the answer right there. But when it's asked in terms of this, solve this differential equation, well, all we have to do is our differential equation is going to be an answer where it says y equals something. It's going to actually equal the linear combinations of those. Okay, so it's actually going to equal c1 e to the negative x plus c2 e to the 4x. It's pretty much the same thing. That's what the span of those guys happens to be. So this right here is the solution to this differential equation. And not only that, when we have a linear nth order, or in this case second order, homogeneous differential equation, you are actually finding a vector space of dimension 2. This is a vector space of dimension 2. I mean, we can see that right there is, well, when I say vector space, it's a subspace of a bigger vector space, but it's a vector space within a vector space. And so solving differential equations like this that are homogeneous, you're really looking for the kernel, you're really searching for a vector space. And so that is how the linear algebra and the differential equations come together. And when I took my first differential equations class, I did not know about linear algebra, and a lot of the stuff they gave us happened to be cookbook, recipe, magic. I mean, I did a good job in the class, but I didn't really see where things came from. And maybe you're sitting there going, I still don't see where things come from, and Joe just makes it more confusing. That could be the case. So let's go ahead and do our next problem. Our next problem happens to look like this. It's the problem that we just did. Okay. So why would I give you the same problem? Well, this is second order homogeneous linear differential equation. The general solution looks like this. It's also an explicit solution because it says y equals. And what the new part about this problem is I'm going to give you an initial value problem. And I want to make sure we know how to solve one of these because we've never done one in this class. So to solve this initial value problem, we have two initial conditions, and we are going to plug them into our solution, our general solution, to get a particular solution that won't have the CIs anymore. We'll have numbers like, you know, a 7 and a 5, but that's, I didn't tell you the correct answer there. So to do this, I need not just this general solution because I have y of 0 equals 4, but I need y prime. So I'm going to go ahead and find out what y prime is. So I'm doing this to the general solution. So y prime is negative c1 e to the negative x using a little chain rule plus 4c2 e to the 4x. Now we don't want to go, oh, 4c2 is just c2 because we have a c2 up there. So we don't want to start mucking around with our ci's at this part. So I'm going to go ahead and put this guy right here, where? Up there. And I'm going to put that guy right down there. Oh, purple and blue. They're almost, yeah, maybe I should have picked a different color. And so on this one, this says x is 0, y is 4. And then this one says x is 0, y prime is 1. Okay, so this one's going to give me 4 equals c1 e to the 0, so then it's going to be plus c2. And then this one's going to give me 1 equals, and I'm putting 0 in for x, negative c1, and then plus 4c2. So I could actually write an augmented matrix. I'm not going to do that. I'm just going to add those together, and I have 5 equals 5c2, and the c1s are out of there. c2 equals 1. and I'm going to plug that back into one of those equations, and I'm going to end up getting lots of arrows. End up getting that C1 equals 3. So this initial value problem has a particular solution. So it seems like I'm just going to rewrite this guy right here with the CI values. So that's what we're going to write here. We're going to write y equals, let's see here, C1 is 3e to the negative x, and then we have plus 1e to the 4x, so plus e to the 4x, and that solves our initial value problem. Let's go ahead and do problem number 10. Oh, look at problem number 9 first, and we'll compare it to problem number 10. It looks like the left-hand side is the same on both of those problems. It's the right-hand side that's different. And because this says 15e to the 4x, that makes this differential equation here non-homogeneous, and this differential equation here is homogeneous because there's a 0 on the right-hand side. So let's take a look at what we have here. At the bottom of this page, you see this linear system that looks like ax equals b. And we have this in linear algebra, and our big theme was that the solution to this non-homogeneous linear system, if b was not 0, would be the homogeneous part plus the particular part. Well, the same thing's going to happen up here, where we're going to say our solution. Now, we're not going to learn how to solve this in this section here, but we can realize that the same thing's going to happen. It's going to say y homogeneous plus y particular. So the first thing you would do to solve this non-homogeneous differential equation is to consider if there was a 0 there and solve for y sub h. So there's one bad thing about this, is this right here. That y sub h in differential equations, they call that y sub c. Now what is y sub c? Y sub c is sometimes referred to as the complementary function. And what is the complementary function? It is the solution to the associated homogeneous differential equation. Okay, so that is so this is called the complementary function, or the complementary solution, instead of calling it the homogeneous one. They just call it the complementary one. We could still call it the homogeneous solution. And it's the solution to the associated homogeneous differential equation. That means if there was a 0 there, basically what it means, it happens to be this solution right here. So I'm going to go ahead and write that down, because I actually kept the same thing. So this yc happens to be, what is it? It is c1e to the negative x plus c2e to the 4x. And so that's what yc is. And we did that. This is from the last few problems. Now, this guy right here is any particular solution. And so we'll underline that particular solution, or particular function, usually called particular solution. Sometimes they'll call this the trial solution. And yp, we don't know how to do. Now, when we learn about annihilators and variation of parameters, we could verify this, but right now, I'll just tell you what it is for this. It is 3xe to the 4x power. And so I did this using the method of annihilators, which we have not learned yet. So if you add both of those solutions together, just like you did back in linear algebra, you end up getting the solution to the non-homogeneous differential equation. Let's go ahead. Okay, so these were kind of new definitions: associated homogeneous differential equation and, complementary function, particular solution. We'll be using those again and again. We're going to do one last problem, and that will complete 8.1. And so our last problem, we're given a second order differential equation. By the way, this is non-homogeneous differential equation. Find the operator equation. So the operator equation, so this is going to be weird, and maybe you just need to see me do this and then you'll go, oh, okay, because they'll ask this in the homework, is the operator equation is we're going to take a look at that side and write it in terms of those derivative operators. And I see a y double prime, it's really going to have, that's the second derivative acting on y. Okay? So now we have to write this one down. This is going to be minus 4x, and then we have d, and so that's the derivative of y, which is y prime, and then this is going to be minus 5e to the 2x. Ooh, that was a close one there. Okay, so that is the operator notation for the operator equation, and this equals sine x. Now, some of you might say, hey, don't we have to solve this? We don't know how to solve this now. This is just trying to get us used to some of this notation and vocabulary. The last one says, find the associated homogeneous differential equation. This is kind of dumb, but if you were going to solve this, maybe the first thing you would do would be to write this down. And so that would be, it's pretty simple to do. Y double prime minus 4x y prime minus 5e to the 2x y. And so this is going to be replacing that sine x with the 0. And the hope would be that by doing this, I mean, we're done with this problem, but the hope would be by doing this, this would tell you what the complementary solution is, which is really the homogeneous solution, and then some other method, maybe annihilators, something that comes in later on, would tell you what the particular solution would be, and then this right here is the goal. That would solve that differential equation. Well, that concludes 8.1. Have a good day.